In this lab, I will be discussing oscillations. There are four main objectives in this lab. Analyze motion of a spring mass system in tracker, using GlowScript, construct a computational model, compare the predicted versus observed motion, and to plot the energy changes. The two key concepts we'll use in this lab are the momentum principle, which states that change in momentum is equal to net force times the change in time, and the energy principle, which states that change in energy is equal to the work. Here, my spring mass system is pictured in tracker with all of its plotted data points. To the right is a graph of its oscillation, and below that is the time and its x and y positions at each time. Our system includes the spring, mass, and earth. Spring and weight force are acting on the mass in the y direction only. Some initial conditions we'll need to code in GlowScript include the period, which was initially found using the 3 periods on tracker. We use the period to find the spring constant and the rest length. And we'll also need our energy formulas pictured to the right. The formulas for kinetic energy, gravitational potential, as well as spring potential. And pictured next to that is our mathematics for how we found the period as well as the spring constant and then the rest length. Because the system includes the spring, mass, and earth, no outside work is being done on the system, so the addition of the energy changes will amount to 0. For the first part of my code, in line 44, I adjusted the ball's mass. In lines 47 and 48, I changed the initial position and velocity according to what was found in tracker. In lines 75 to 81, I inserted the initial conditions which were discussed on the previous slide. In lines 84 to 86, I changed these values according to the lab instructions. And in lines 89 to 92, I inserted the energy formulas for kinetic, gravitational potential, spring potential, and then the addition of all 3 of those for total energy. In the second part of my code, for lines 184 to 187, I set the initial energies equal to the formulas. In lines 110 to 116, I calculated all of the forces, which included gravitational, spring, and then net force. In lines 120 to 122, I inserted the update equations positioned below, which is for final velocity and final position update. In lines 125 to 127, I updated the spring, the length, L hat, and the stretch. In the final part of my code, for lines 133 to 140, I calculated the energy changes in the system. I used the initial values and the values found in the while loop in order to get the change in energy and the total energy. Pictured here are my graphs generated by GlowScript. On the left, I have my position versus time graph for the predicted versus observed position of the spring mass system. As you can see, the graphs do not perfectly align. This could be due to any number of errors such as human error, the count in the GlowScript code itself, or a change in rest length in the code. Pictured on the right, I have my change in energy versus time and a simulation of my spring mass oscillating above that graph. The blue line represents the change in kinetic energy. The red is the change in gravitational potential. The green is the change in spring potential, and the orange equals the change in total energy. So gravitational potential is balanced by spring potential. So when the gravitational potential is positive, spring potential is negative, and the addition of these two values as well as the change in kinetic all sum to 0, as discussed earlier. Kinetic has a smaller frequency but approaches 0 when it reaches the end of its semicircle trajectory from swinging. What does it mean? Is the energy principle satisfied? Yes. As discussed and shown in the graphs on the previous slide, the change in total energy amounts to 0, meaning there is no external work being done on the system because the system includes the spring, mass, as well as the earth. The sum of the total change in energy is equal to the change in all of the energies present, which include gravitation and spring potentials, as well as kinetic. Are the x and y period oscillation estimates the same? Yes. Because the mass is oscillating as opposed to translating, the time that it takes to make one full oscillation between the x extrema is the same time as for the y extrema. This is because they both are reached at their same time respectively in the swaying trajectory of the mass.